Hello, our most valued student. My name is Confident. Welcome to our revision session, and this is Engineering Science N2. And the topic that I'm looking at today is heat, and I'm just looking at a complete guide. Hopefully, I'll do part 2, but even this part 1 on its own is very sufficient because the examples that I'm giving in here, there are quite a lot of examples that I'm going to be covering. So I hope I will also do part 2 of this lesson where I cover more examples on the topic of heat, and it is one of the most important topics if ever you are doing your engineering science N2. So the more questions I'm covering, it kind of give you a holistic view of what is required as you are doing the topic of heat in your engineering science N2. So again, guys, if this is your first time coming in contact with this channel, the 24-minute lesson, I will encourage you to subscribe to our channel so that you can be notified every time we post a new video. You can also turn that notification bell on so that YouTube notifies you in real time every time we post a new video. Also, remember to share this channel to your friends, to your colleagues. Remember, guys, sharing is always caring. And also, if you've got some questions that you want us to attend, or if you've got some ideas, some feedback just that you want me to be aware of, you can always leave your comments on your on this channel, and I will respond and get back to you. Most of the things that I'm doing here is because of the feedback that students are giving, so it gives me kind of an idea what is required instead of just teaching for the sake of teaching. So mostly I teach due to the demand of some of the topics that students are bringing. So now let us look at this lesson again, and as I said, the topic is heat, and it's a complete guide, meaning I'm just going to do as much examples as possible as far as this particular topic is concerned. So I'm taking these, as you can see, from past papers, and I'm using, in this case, the paper that I'm using here is a paper, I don't have the year here, but you can see this is the topic that was on heat, question number 7. So mainly it's question 7, and that question 7 is the question that focuses mainly on heat. So this is what we are looking at here. Now let us look at the question, and then we will go through the answer. It says 7.1 here. It says we are supposed to name 3 forms of combustibles and give 1 example of each. So when you're going through this topic, you will come across combustibles, mainly fuels. So there is 3 forms. By saying forms here, the keyword there that you need to take note of is the forms as well as the combustibles, more like 3 forms of fuel. So now what you're given here, there is it's always a question that they like asking, but now this one is 6 marks. Says name 3 forms of combustibles, and then it says give 1 example of each. So which means when you are naming them, you'll be given a mark, and then when you give an example, you'll also be given a mark. So be careful how you answer this particular question. So I'm just going to answer it here to say the 3 forms. The first one, it's solid, is the first form. The second one is liquid. I'm just naming, I think you know the 3 forms, the state of matter. So that is a common question, the 3 states of matter: the solid, the liquid, and the gas. Sometimes the liquid, in this case, they usually use the word fluid. So these are the fluids in this case. So now they said you need to give an example of each of these. Now let's start with the first one. If you can remember, the word combustible means something that can burn, and that's why I said fuel is the keyword. Now any solid fuel that comes in your mind, we use wood as a fuel. So just one example, you could have said coal as an example. You could have said sometimes coal can be interchanged with charcoal. Just anything that is solid that you can use for burning, that's a combustible. Now for the liquid that you can use as a fluid, this is plenty. You use your diesel here, you use your petrol, it's fluid. You use your paraffin, just this is a lot. Like you use your oil, it still fits under that. And then when it comes to the gas, also remember the gas that you use in the houses when you're cooking with a gas stove, that is methane. We use there is also butane, it can be a gas. Then there's the acetylene. There is the acetylene gas, the gas bottles, the oxyacetylene gases, and then any gas, propane, all the organic gases, propane, butane, octane, anything that is actually octane is not a gas, it's actually propane, butane, and methane. So these are three forms, in a way, three states of matter, but in this case they call them combustibles. So they are solids, they are liquids, and they are gases. So it's 6 marks, and to me this is a good 6 marks. 6 marks if ever you are working on that. Now the next question says here, 7.2, it says a petrol backup generator is used at a hospital. Let me just erase. It says a petrol backup generator used at a hospital took over for 2 hours during load shedding and used 20 kilogram of petrol. So we've got 2 hours, we've got 20 kilogram of petrol. So they're saying a petrol backup, so we're dealing with petrol. It's a generator used at the hospital, took over for 2 hours during load shedding and used 20 kilograms of petrol. And then it says assume 35% of heat was lost, not gained but lost, due to incomplete combustion. Now it says calculate the following. Number 7.2.1, the amount of heat released by the petrol. So in this case, whenever we are dealing with the amount of heat that is released by petrol, it is very important for you in this case to grab hold of the formulas. So you have the formula sheet as well as the constants and the information sheet. So I'm just going to show you most of the things that you are going to find in the information sheet. So this is my information sheet that I'm using here, and now it is very important for you to be familiar with this, and especially when it comes to number 6 here where we got a lot of values. And if I go back to the question, we are dealing, in this particular case, we are dealing with a question on petrol. So they will always give you a question that is familiar. So we are dealing with petrol. So if I come here on this information sheet, you will discover that there is information concerning petrol. The first one, if you look at this part, there is the heat value of petrol, which is very important, that part, because we're dealing with petrol. And they, as I said, they will always give you some information, so you need to know that. The other part, you can check the specific heat capacity. That is another important information that you need to know. And then the linear coefficient expansion of steel, as well as these three materials. So from here, in a way, if I can just say, from this part actually to that part, this is the part that mainly deals with heat. So you need to be familiar with these values, including the density of water as well as the heat value of coal. Actually, even this part is very, very important for you. So this is the information page. If we go also to the formulas, at the back of your paper you'll be given formulas. Now there is quite a few things that you need to be aware of. The first one, it is that part, which is the efficiency, which is output over input as a percentage, as well as we need to know this formula, which is heat energy is MC change in T, which is mass times specific heat capacity of that substance times the change in temperature, as well as these two formulas also when you're dealing with expansion in terms of change in length, as well as the final length is in original length plus or minus change in length. So these are the few formulas that I'm just trying to quickly familiarize with, but it is very important for you to go through your textbook just to get a basic understanding on the topic of heat. So now let us go back to this question 7.2. It says a petrol backup generator is used at the hospital. Took over for 2 hours during load shedding and used 20 kilogram of petrol. Now assume 35% of heat energy was lost during the complete combustion. Calculate the following. So what are we calculating? The amount of heat released by the petrol. So how do you calculate the amount of heat? Remember, the amount of heat can be calculated by the letter Q. So Q is equal to mass. There is a formula which says mass times the heat value, which is HV. So if you multiply mass of that particular substance times its heat value, you're going to find the heat released. So let's assume this was the heat at 100%. So the heat at 100% is the mass of coal, which is 20, times the heat value. Now let's go to the formulas and you will find that the heat value of petrol, you see, they did give us, it was that number, 25 megajoules per kilogram. So if I use that number times 25, my answer here will be equal to, if I multiply the two, so I'll be having 20 times 25, and then remember I am dealing with megajoules, so it's 500, because these are large numbers. It's 500 megajoules in this case. So don't think you end up in error and writing your answers just in joules. So it's 500 megajoules. Why? Because the units of measurement on my heat value, you can see they used MJ, so you also need to maintain the same units whenever you're calculating that. So that is the first part. But they mention something. They say assume 35% of heat was lost. So if 35% of heat was lost from 100, it means 100 minus 35%, which was lost, is equal to 65% of heat was used. So which means the efficiency was 65%. So now you need to find 65% of the 100% of heat. So which means you're going to say 65 over 100 times 500 megajoules, and then it will give you now the heat that was actually used by the petrol when it was running for those 2 hours. So if you can find that, what you're going to have in this case, if I can just grab a hold of my calculator again there, what I have here is 65 over 100 times 500, and it gives me in this case 325. Remember, you're dealing with megajoules. So this is the part when they say the amount of heat released, we are talking about the amount of heat that had complete combustion. Remember, they said 35% was incomplete, so you must take out the 35% so that you are left with 65%. Or what you can do, you can find 35%, which is 35 over 100 times 500, and then if you do that, it will give us, if I can just check that, 35 over 100 times, so if I can say 35 over 100 times 500, I'm getting 175. So it's 175 megajoules. So you see, this 175, remember, is not the final answer. Now this was lost, remember. Now what was useful, you subtract from 500. So if you say 500 minus 175, then it will give you 325, which is back to that answer. So now the answer in this question is 325 megajoules. That's 7.1. So now if I can erase so that I can do the next question. Now the next question says the power output of the fuel. So now if we want to find the power output of the fuel, to say how efficient is this particular fuel or the generator, remember, when you're dealing with power, is equal to, if I can go to the formulas and look for the formula for power in these formulas, you can see that power is work done over time taken. So if I can use that formula for power to say P in this case is equal to work done over time taken, but now work done is measured in joules. So another way for saying work done is to say energy over time taken. Now what is the energy? We said the energy used was 325. Remember, we're dealing with megajoules. These are not SI units. Divided by the time taken, they are saying 2 hours. Now since we are now calculating power in this case, it is wise now to use the standard units. So I'll say 325 mega means times 10 to the power 6 divided by 2 hours, which is 2 times 60, which is now minutes, times 60, which is now seconds. You must convert that time to seconds. If you do that, then you need to use a calculator now for you to be able to find the actual power. In this case, it is 325 times 10 to the power 6 over 2 times 60 times 60. And then if you do that, you will get that the answer in this case was 45,138. You can divide by 1,000 if you want. So it's 45,138,89. So it's 45,138,89. And you know what is that? Remember, this is the SI units, so the units will be watts. So you can further divide by 1,000, which is 45,14 kilowatts if you want, or you can divide by 10 to the power of 6 or a million. You can change it to megawatts. It's up to you. So, but be careful that you convert your units to watts. Your units to SI units here to say the energy was in joules and the time was in seconds, and then joules per seconds is the watt. So guys, this is one example that I was bringing. Let us look at another example that deals in this case with heat. So there is another question that I just took from previous papers, and it's question 7 also, and then this one I think was written between 2017 2016, somewhere there, but as you know, this syllabus has not changed. Now 7.1 says give 2 forms of combustibles. Now this is 2 marks. We have already looked at this one. It is similar to the previous one. The 2 forms here, we said there are 3 actually. They just want the forms now: the solid, the liquid, and the gas. So now the previous one was saying even give examples of that. So that is that part. Now the next part says a 40 kilogram steel rod with a temperature of 8 degrees is immersed in water at 20 degrees. What mass of water is required if the final temperature of the mixture is 60 degrees? And then you get 3 marks. Now let's say I have got a page that I want to use here, just to show you sometimes how these calculations you can approach them. So how do you analyze a statement like that? First, they're saying a 40 kilogram steel rod. So you've got steel rod, it is immersed in water. So you've got 2 kind of materials here. If I can divide my page, so what you have steel. Let me use another pen. So I have got steel this side, and then on the other side I have got water. Alright, so these are the 2 different materials that I'm having in this case. So the steel is that one, and the water is on the other side. Now let's look at the information that they're saying. The information I'm given is a 40 kilogram steel rod. So we say the mass of the steel is 40. So you come here to say the mass is 40 kilogram under steel, and then with a temperature of 80 degrees. So you come here and say the temperature, which is T1, is equal to 80 degrees Celsius. That's the first temperature we are told, and then is immersed in water at a temperature of that. So that is the temperature of water. So if I go now to water, I have got a temperature, it says is immersed in water at a temperature at 20 degrees Celsius. So this is the temperature. The 20 degrees Celsius refers to the temperature of water. So I come to water here, which is my T1, is 20 degrees Celsius. And then it says what mass of water is required if the final temperature of the mixture is 60 degrees. So we've got the final temperature here. For the T2, they're saying the temperature dropped down from 80 because it was hot to a cold environment. So it was from 80, the final temperature was 60. But for the water, it increased, it was at 20. And T2, they're saying the system now, or the whole mixture, was now 60 degrees, meaning the temperature of the steel and temperature of the water was that. So the question here wants us to calculate M. That's what it wants. But now there is information, as I said, that you need to already know whenever you're dealing with this part. The first part of the information you need to know is the specific heat capacity, C, in this case of steel, and the specific heat capacity. So C here is the specific heat capacity. Are you with me? So you need to know the specific heat capacity, so the C of steel, and then we need to also know the C of water. So we are given that information. If you go to the formulas that we use, the information page that we have, we had the specific heat capacity. If I can just take this off so that you can see what I'm referring to. There is the specific heat capacity of steel is 500, and the specific heat capacity of water is 4187. It's joules per kilogram degrees per kilogram per degrees Celsius. So it's water, steel is 500. So if I can have that to say, for steel, what I have here is 500, and then for water, it's a common one, is 4187. Just to verify if it's correct, but it's a common one. All right, so this is information that you need to know. It looks like you've got less information, but through that you can actually see that you've got quite a lot of information. Now the question is, what mass of water is required if the final temperature is that? So we're looking for the mass of water. Now remember the formula that we said we have. This is the formula we're going to use. Q is equal to M times C times change in T. We're going to use this formula on both sides. The first one here to say Q is equal to M dot C dot change in T. So even here, Q is equal to M dot C dot change in T. So now we divided our line. I'm just dividing so that it can show that I didn't mix I don't mix up the formulas and then the numbers. So you can actually say Q of steel and Q of water in that case. So meaning the energy released from the steel and the energy gained by the water. Remember, the steel is releasing the energy because it was hot to cold, so it released, or it lost energy, but the water gained energies, so it is absorbing the energy from the steel. So using that information, we can then say our Q in this case for steel is equal to the M is 40. You can see it must be in kilograms. The specific heat capacity, they say it was 500, and then the change in temperature. Now it's up to you how you want to do it. You can come here, exactly here, and say what is the change in temperature. Now it's T2, which is if I can write it like this, change in temperature is T2 minus T1. So what is my T2? It's 60 minus 80. So you are tempted to say the answer is minus 20, but ignore the sign and then you just write the positive one. So even if it's negative, just write 60 minus 80 is same as 80 minus 60. Since temperature, in this case, we are calculating the change, the answer has to be just a positive one. So it's 20 degrees. So you are going to have here times 20 from 60 minus 80. And then if you do that, you'll get the answer to say, if I multiply 40 times 500 times 20, it's going to give me, in this case, it's 400,000. So I've got 400,000 here. What about on this other side, the Q of water? I do the same thing. All right, before I do that, now remember, this is joules. This is what was lost Now we know the conservation of heat to say heat lost is the same as heat gained. So here we assume no heat was lost because all the heat lost was gained by water. So here we are saying it was gained, so which means water gained this amount of energy, which means where there is QW now you have got 400. That's where you have got 400,000. That is the heat that was gained from the steel, is equal to M dot, the specific heat capacity of water is 4187 dot. Now the change in temperature is the same thing that I said previously to say when you're talking about change in temperature, you look at this, says change in temperature is T2 minus T1, which is equal to T2 is 60 minus 20, so the answer here is simple 40 degrees Celsius. So you multiply that by 40. So now it's up to you now how you solve the equation. And in maths, I think you know to say whenever we want to find M, we have to divide by what we don't want, which is 4187 times 40, so that the 40 cancels, the 4187 cancels, but what you do on the left you do on the right. 4187 times 40. So if I do that, it will give us now our M, which is 400,000 over it's 4187 times 40. Remember the mass that you're going to find is, which is 2,388, which is 2,39. It is therefore 2,39. Now the units of mass is kg. Don't forget that you're dealing with kgs. So is equal to M. So the question was, if we go back to say what mass of water is required if the final temperature. So the mass of water that is required there is the one that we calculated to be 2,39 kg. Are you with me? And then 7.3, and then says ice at minus 20 degrees Celsius changes to water. Indicate the changes graphically and explain in words what happens during each of these changes. So when you are dealing with ice at minus 20 degrees, this is a common graph, but here they wanted to restrict a few things here. So if I can just quickly show you, what they are saying is, are you able to plot or kind of draw a graph like that to say, if we are given, there is a graph, it's a common graph on the phase changes of water. So if that is 0 degrees, and then at that point is minus 20 degrees, now you need to pinpoint how are these, if you remember, to say from 20 to 0 here, and then from there we have that straight line like that, and then we have a new phase that is going to be coming in from here to say that they were just interested in ice melting. So we are saying from 0, this is ice, and then this is melting. This is ice melting in a way. That's what you can say ice melting, or you are actually saying from ice to water. That's what is happening. So from ice to water. So what is happening, the question here says ice at negative 20 degrees changes to water. Indicate the changes graphically and explain in words what happens during that part. So this is the graph that they want. They want to show from negative 20 to 0. So you can say from, we can call this part maybe A, B, and C. Then you tell us from A to B what is happening. You are saying the water is in ice form below 0 degrees. So water is in ice form below 0 degrees. That's the first part. And then from B to C, ice is melting, that is changing from solid to liquid, but at what? Look at the horizontal line, then you say at constant temperature. at constant temperature, pardon my writing, at constant temperature of 0 degrees Celsius. You understand? So from A to B, you can actually even indicate that the temp is increasing. That's what we're noting. And as the temperature is increasing, that's when we're saying ice is changing from what? From solid to liquid. The moment it starts changing to liquid, it is at a constant temperature until the end. So that is that part of what they needed. It was 6 marks, but I will encourage you to gain knowledge of that graph. It is there in your textbook, but another question that comes, or I will have a tutorial that focuses just on that graph. But because of time, let me move on to the other question. Now in this one here for today, I think I'll end up here, and then I didn't want to do part 2, but I will be forced to do part 2 because of time. Now define the term heat capacity. Now heat capacity is the amount of heat needed to raise, this is heat capacity, not specific. Remember, there is the specific heat capacity. So the heat capacity is the amount of heat needed to raise the temperature of the whole substance. Now, not just a 1 kilogram of substance, but in this case is the amount of heat needed to raise the temperature of the whole substance by 1 degree Celsius. That's the heat capacity. Okay, so it's the amount of heat needed to raise the temperature of the whole substance by 1 degree Celsius. The next question is, a welder places a steel workpiece which has a temperature of 90 degrees into a container with 0.5 kilogram of water at 30 degrees. If the final temperature of the system is 50 degrees, calculate the mass of the steel workpiece. Similar question. What you do here, you divide, have a new page whereby you divide it and say, if I can have, they are dealing here with what? It says you are dealing with steel workpiece and you are dealing with water. So if you can have that to say, if I can have steel this side and I get all the information, and I can have water this side, I get all the information. It's good if ever you have to write it in different forms, just to I'm writing it in different forms so that you can see. It says a welder places steel workpiece with a temperature of 90 degrees. So if I come here, the temperature T1 is equal to 90 degrees Celsius, and then into a container with 0.5 grams of water at 30 degrees. So here 0.m is equal to 0.5 kilogram, and then T1 of water, they're already telling us that T1 is 30 degrees. You can see that. So that's what that information you need to utilize. It says if the final temperature of the system is 50 degrees Celsius, calculate the mass of the steel. Now they want the mass of the steel. So T2 is equal to 50 degrees Celsius. And then also they're saying here, if the mass of the system, so even the water here, T2, it is also equal to 50 degrees Celsius. It's an equilibrium. After some time they have the same temperature. Now the question then says here, calculate the mass of the steel. Remember, whenever you are dealing with the steel, we say the formula to use here, you say Q is equal to MC change in T. Even here Q is equal to MC change in T. But now the Q of water, the heat lost, actually is the heat gained from the water. We know the mass is 0.5, the specific capacity 4187 of water times temperature, change in temperature. You can come here and say T2 minus T1 is equal to change in temperature. What is T2? Which is 50 minus 30, which is equal to change in temperature. So 50 minus 30 is 20. So the change in temperature there is 20. If you can do that, it will give you the final answer to that. And if you can just check your final answer, it's 0.5 times 4187 times 20, and then you get, in this case, 41,870, which is 41870. Now remember, in this case we are dealing with joules. Now we come here, we know that what was gained, this is what was gained, but at the same time it's the same thing that was lost. So you take that 41870 is equal to the M, which we don't know, times the specific heat capacity of steel. I think that's what we underlined here to say is 500. We got it on the previous question to say times 500 times. Now changing T, here it's T2 minus T1, which is 90 minus 50. As I said, ignore the negative sign, which is 40. So you multiply by 40. So here you'll divide by 500 times 40. Even this side, 500 times 40. When you do that, it will give you your M of steel. Remember, it is in kilograms. So that's how you have to simplify that answer in that. Now, I would have loved to continue, guys. Just my time does not allow. I have to end up this lesson. But I just wanted to bring to you some of these questions to say, look at how easier it is to manipulate these questions. In the next part, definitely there is a part 2. I will continue again this question. Question 7 started from this calculation where we were dealing with 7.2.2. Then I continue from 7.3, whereby it says a 20 kilogram mass of coal is used to boil 1,200 kilogram of water from 30 degrees. Calculate the amount of heat released by the coal. Calculate the final temperature of water if 35% of heat is used to heat the water. So this is what I'm going to look at. And there is another question also that I didn't look at. It is this particular question, and which means I'll also do more questions in the second section. And it was tabulate the difference between heat and temperature. A steam boiler uses 50 kilogram of diesel to heat water of 1000 from 20 degrees to 60 degrees. Assume heat value of diesel is equal to that of petrol. Then they ask all these questions. These are the questions that I'm going to deal with in the next section. So stay tuned, watch out. That's why I say subscribe and make sure that the notification bell is turned on so that you're notified every time there's a new video. We've come to the end of our lesson. Thank you.